So in the first tutorial video, basically I was explained the ID versus VDS curve of N-channel MOSFET. So we was explained that we have three regions and we consider our VDS is 400 millivolt. 400 millivolt. So if we maintain 400 millivolt drain to source voltage and increase our gate voltage, so for different gate voltage I get different curve. So this is the maximum gate voltage that I'm applied into my MOSFET, which is 800 millivolt. So the summary is that when your VDS is fixed and you will increase your gate voltage, in this case your drain current will be increased, and based on your VDS or your overdrive voltage, you can perform your MOSFET in three regions. So whenever your VDS is very lesser, in that case your region of operation is linear or triode region. But whenever you increased your VDS, your region of operation will be changed, and this region is called saturation region. Suppose you consider a large amount of VDS. Let us consider 800 millivolt, for example, 800 millivolt. But your gate voltage is 0. So it is actually means that your MOSFET is actually under your threshold voltage of this MOSFET. So for this region, your MOSFET is basically turn off. It's actually not biased. So for this region, you cannot get any current. Your MOSFET is actually open. So in this happening situation, we called cutoff region. So these are the three regions that I am discussed the last class. So now we will see what is the relationship with length of this MOSFET, this NMOS. So if we change length, what will be the impact? So let's try to see this. So for this region, I go to the parametric analysis again and insert a new row and add a new variable that is ln, because I want to sweep my length. So my minimum length for 90 nanometer technology, which is 100 nanometer. And for example, I consider 5 micro with 5 step size. So Let us disable the VG. Now we sweep just length, and let's try to see what will happen. So you can see that we have uh, 5 different length and corresponding curve. So this is the red curve, which is maximum here. So suppose our VDS is 400 millivolt, 400 millivolt, and we want to operate in saturation region. So this is the point for the saturation region. So in this case, I get my maximum current, which is 8.22148 microampere. And this current, I get maximum here. And the other, also I have some current, but they are actually very lesser than this red curve. So if you see that for this red curve, your length is actually minimum. So your length is actually minimum, that is 100 nanometer. And your current is actually maximum in this case. If you increase your length, for example, for this curve, which is 1.325 micrometer, in this case, your current is some sort of nanoampere range. And if you further increase your length, your current is actually decreases. So now, what will be the comment? So the comment is very straightforward and very simple. That is, if you increase your MOSFET length, in this case, the MOSFET finite output resistance will be increased. So if you increase your channel length, the resistance of your MOSFET will be increased and it will reduce your current. So we can observe this in this case. So this is the 5 micro. In this case, you can see that the current is actually minimum level here. So if you need uh, a good amount of current, you can choose your MOSFET length minimum. In this case, your resistance will be lower. You get larger amount of current. So this is the relationship with length. But now I will explain this curve furthermore. So let us change the gate voltage. Togetherly, the VG and L and I sweep togetherly. So please try to be patient. Okay. So we get our curve. Let's expand this and try to understand what will happen. So here this column is for VG, that is your gate voltage, and this is your column for your length. So we consider here 5 different type of gate voltage and its corresponding channel length. So that also varying. and try to interpret what will happen. So when your gate voltage is zero, so nothing to do, your MOSFET is actually turned off. So if you use minimum channel length or maximum channel length, whatever, your current is actually flowing leakage current, which is very negligible amount, picoampere range. You see that here, nanoampere range. So that is called the leakage current. If you apply some sort of uh, higher voltage than your threshold voltage, in this case your MOSFET will on, and by based on your VDS, your MOSFET will work as triode region or saturation region, whatever. So basically, I want to explain these things. That is for this curve, uh, for 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 this value 0.2 volt or 200 millivolt, I consider maximum channel length, which is 5 micrometer. Okay, and for 400 millivolt, I again choose the length 5 micrometer. For 600 millivolt, I choose the length similar, which is 5 micrometer. And for 800 millivolt, I choose my length similar, that is 5 micrometer. So what you can understand from here. So if you see that this curve, your gate voltage is minimum, that is 200 millivolt. And for this curve, you increase your gate voltage. And for this curve, you increase your gate voltage furthermore. And for the last curve, you increase your gate voltage roughly 800 millivolts, so more than before all values. So what will happen here? Let's try to understand this. So if I hide those things and consider these things, so in this case also you can see that whenever your gate voltage is higher and you use here your channel length is basically very larger, in this case your um, current is maximum compared to others. So for 600 millivolt, your current is in nanoampere range, current is reduced. For 400 millivolt, your current also reduced, that is 9.71 nanoampere. And for 200 millivolt, it also uh, reduced, which is um, so for 200 millivolt, it is actually also reduced, which is in nanoampere range. So from here, we can interpret that if we maintain a long channel, in this case, what will be your VG? It may be a higher value like 800 millivolt. The happening is that you cannot get much current. So the conclusion is that very simple and very straightforward. That is, if you increase your length of your MOSFET, what will be the gate voltage? the current will be reduced. So this is the conclusion of this curve by based on length and the gate voltage in the output characteristics curve of this NMOS. So we can hopefully understand this scenario. So I think you can understand these things. So now I will move for the next part. So now basically we try to understand what is the relationship with width of this MOSFET. So for this region, I close this window and again insert a new row and add here WN, that is the width of the NMOS. And the minimum width is 120 nanometer. And I consider, for example, 8 micro. And total step size, let's say 8, or let's say 10. So let us disable the VGNLN. Now run the simulation. All right. So this is your curve for different width. So if you see here, for example, you consider 300 millivolt, your VDS. Your VDS is 300 millivolt. So in this case, to get much current for this orange curve. So here the width is 120 nanometer. So the width is minimum to get minimum current. You get minimum current, and the current is very small actually, 7.1 microampere. So if you increase your width, you can see that your current will increase. Your current will increase. So you can see I increase my width, my current will also increase. So what does it mean actually? So basically this implies that your width of the MOSFET is actually increase with your current. If you increase your MOSFET width, then the drain to source current will be also increased. So they are actually not inversely proportional or vice versa, but roughly you can consider they are actually proportional. Proportional means not linearly actually. Proportional means if you increase your width, your current will be increased. So that's it. So the relationship is the width is like this. So what does it mean actually? Whenever you increase your width, the resistance of your MOSFET will be decreases. So in this case, your MOSFET allow much current or much current. Yes, much current. So finally, I will sweep the VG with WN togetherly. And try to understand the relationship in between the uh, gate voltage with the width of the MOSFET. How do they actually connected? So it takes some times. Um, all right. So okay. So here I am get my curve. So you see here tons of curve. So we need to understand this. Uh, so let's uncheck all the curves. So at first I consider my all the minimum width for my lesser VG, that is 0 volt. And now I increase my VG 200 millivolt for the width 120 nanometer. And then I will increase my gate voltage. And we increase this into 400 millivolt, like here, and then 600 millivolt. So for 600 millivolt, this is your point. And then for 800 millivolt, this one. So you cannot understand this curve very well manner. So because of your width is actually very lesser for this region, your current is actually not higher. But interesting thing is that you apply here a larger gate voltage, 800 millivolt, but your width of the MOSFET is very lesser, 120 nanometer. So for this case, you apply a much gate voltage like 800 millivolt, 600 millivolt, 400 millivolt. You cannot get much current. But if you increase your channel length, if you increase your width, and let's try to see the uh, curve. So suppose I consider for 8 micro. So for gate voltage 0, my width is now 8 micro. Now my gate voltage is 200 millivolt. My width is 8 micro. For 400 millivolt, my width is 8 micro. And then for 600 millivolt, my width is same, 8 micro. And for 800 millivolt, my width is actually 8 micro. So you can see that now I am using here same width for different gate voltage, like 0 volt, 200 millivolt, 400 millivolt, 600 millivolt, and finally 800 millivolt. So you can see that if you increase your channel length, as well as if you increase your gate voltage, your current will be increased. Your current will be increased. So the main thing is that if you consider, say for example, um, 600 millivolt with a larger channel length, like 3.1461 micro. So you get roughly good amount of current, which is 130.6 micro. And if you go furthermore, that means if you increase your drain voltage, your current will be also increased. So finally, we can say that the width of your MOSFET is actually interconnected with your gate voltage, and it will trigger your drain current. So if you increase your width of the MOSFET and increase your gate voltage, in this case, for a certain VDS, for example, for a certain VDS, let's try to consider, for example, 200 millivolt, you get much current. So this is the example that I am using here. My gate voltage is 800 millivolt and my length is 8 micro. My gate voltage is actually 800 millivolt, but my width is actually 8.5 micro. My gate voltage is 800 millivolt, but I reduced my width 3.146132 micro. My gate voltage is also same, that is 800 millivolt, but I reduced my width 1.9 micro. My gate voltage is actually 800 millivolt and I reduce my length in 1.2372 micro. My gate voltage is 800 millivolt, but now my length is 775 nanometer. So I think this example is good enough to try to understand what will happen. If you fixed your VG and increase your width, your current will also increase. So that is the observation. So the tutorial is actually finished in this moment. So I think this tutorial will be helpful for students, and we can understand the relationship between the ID versus VDS with different type of phenomena. So this is the wrap up time. And with this, I conclude this segment. Thank you.